Section 5.3, the fundamental theorem of calculus. The fundamental theorem of calculus means this is considered by mathematicians the most important theorem in calculus. And here we're going to have two of them. One, we're going to call the fundamental theorem of calculus part 1. And what does it say? It says if f is a continuous function on the closed interval ab, then the function defined by, call it g of x, the integral from a to h of x f of t dt, this function here is also continuous on the closed interval ab and differentiable on the open interval ab. And what does the theorem say? It says that if I want to differentiate both sides, what do I get? That the g prime of x equals, we take that function, replace it for every t in this function, so f of h of x times the derivative of h of x, times the derivative of h of x. Keep in mind a is constant, so a is a number. A can be any number, positive, negative, anything. So this is what we need to do, is to make sure the conditions are met, and then we can apply it this way. So let's look at the first example. I want to find the derivative for this function. What's the derivative for this function? G prime of x. We replace every t within that integral by x, so that becomes x squared, times the derivative of x itself, and that gives us the square root of 2 plus x squared. Notice a here is 0, is a constant. What about another example? Let's look at this example here. How do you find g prime of x? We replace every t with x squared plus ex minus x squared plus ex plus 1 times the derivative of the x squared plus ex. Okay, so what do we get here? G prime of x equals, keep this the same, 2x squared plus 2ex minus x squared minus ex plus 1 times the derivative of this, 2x plus ex. So that gives us the derivative of this function. We can look at more examples. All we have been using so far, the derivative, the fundamental theorem of calculus 1 plus z to the fourth dz. It doesn't have to be all the time t, it could be any other variable other than x. So what do we do here? G prime of x. Notice that the lower bound is 1, is constant, so we're okay so far. We replace every z with x, with the square root of x, square root of x to the fourth, times the derivative of the square root of x. So what does that give us? G prime of x equals x on the top, 1 plus x squared in the denominator, and the derivative of this one is 1 over 2 square root of x. Where did that come from? You can rewrite it as we did before, x to the 1/2, and then bring the 1/2 down, x subtract 1, then bring that negative 1/2 down to 1/2, and then that gives you what we need. So then you can leave it like this, is totally fine. Or if you want to rewrite it as x over 2 square root of x times 1 plus x squared, that's fine too. So that would be good. Another example, let's look at other example. G of x equals the integral 0 to sine x, the square root of 1 plus t squared dt. G prime of x is what? Is replacing t with sine x, so sine squared x times the derivative of sine x. That gives us g prime of x equals, this stays as is, and derivative of sine is cosine. So that would be really sufficient. Now, what about if we look at another example? That example doesn't start with a constant. So g of x, let's say it starts with x squared to 1, natural log of t plus 2 dt. So how do you find the derivative? Well, before we find the derivative, from previous sections, we can rewrite the bounds, swap them, 1 to x squared. And when we swap bounds with the integrals, what happened? We put a negative sign in the front. So then we can use the fundamental theorem of calculus 1. It says keep the negative out. It's natural log of x squared we replace the t with x squared, plus 2 times the derivative of x squared. So g prime of x equals negative 2x, that's the derivative of this, times the natural log of ln of x squared plus 2. So if the lower bound is not constant, we should swap it. Now the question, students ask, how about if both the lower bound and upper bound are not constants? So what about if we have g of x equals some function called h of x to k of x, f of t dt? Then what? How do we handle this? How do you find g prime of x? What does that equal to? Well, there are two things. One as a shortcut, and the other one is a step-by-step procedure to be able to apply the fundamental theorem of calculus part 1. And the way this works is that we need to rewrite this as h of x to 0 f of t dt. So I'm splitting the upper and lower bound. Instead of just going from h to k, I'm going to go from h to 0 plus 0 to k of x f of t dt. So we split it as you can see, and then the next thing is, before we start finding derivative, we rewrite the first one by swapping the bounds, f of t dt plus the integral from 0 to k of x f of t dt. Then we can find the derivative. G prime of x is negative the function evaluated at h of x times the derivative of h of x plus f evaluated at k of x times the derivative of k of x. So if we look at an example, let g of x is the integral from x to 1 minus 3x t squared plus 10 dt, and we are asked to find g prime of x. What is g prime of x? Well, notice how the bounds are not, it doesn't start with a constant bound. What needs to be done? X to 0, t squared plus 10 dt, plus 0 to 1 minus 3x, t squared plus 10 dt. Then, next we swap the bounds, 0 to x, t squared plus 10 dt, plus 0 to 1 minus 3x stays the same. So then it's ready for, by the first fundamental theorem of calculus, we keep the negative out, replace the t with x, so it's x squared plus 10 times the derivative of x, plus replace t with x with 1 minus 3x times the derivative of 1 minus 3x. G prime of x equals negative, this stays the same, times 1, plus this one here is, you can expand it, so it's 1 minus 6x plus 9x squared plus 10, and multiply that by negative 3, the derivative. And then g prime of x, we distribute this, negative x squared minus 10 minus 3 plus 18x minus 27x squared minus 30. So that gives us g prime of x, combine like terms, negative 28x squared plus 18x minus 43. So that was an example on the fact that the two bounds are not, neither one is constant. What about a slightly different kind of example? Let's say given g of y, re to y, f of x dx, and f of x is given as an integral from 0 to sine x, the square root of 1 plus t squared dt. Find the second derivative at pi over 6. Find the second derivative at pi over 6. So how do we find the second derivative at pi over 6? So first we start with the first derivative for that function using the first fundamental theorem of calculus. So we start with g prime of y is f of y times y, which is 1 here. So it's simply f of y. Then if I want to find the second derivative for this, the second derivative at y, it's f prime of y. But how am I going to find f prime of y? This is f of x. So to do f prime of y, that would be using the first fundamental theorem of calculus, we replace, you see, the t with sine x. Sine x, so it's the square root of 1 plus sine square x. But since there's a y, I put y, since there's a y here. Times the derivative of sine x, or sine y in this case. This equals, this stays the same, nothing can be done, but this is cosine y. Then we are asked to find the second derivative evaluated at pi over 6. All we have to do is substitute sine square pi over 6 cosine pi over 6 equals 1 plus the sine of this is 1/2 square. This is radical 3 over 2. This is 1 plus 1/4 times the square root of 3 over 2. Inside the radical sign, multiply by 4 by 4. So that gives us 5 over 4 times the square root of 3 over 2. Then this is the square root of 5 over the square root of 4, which is 2 times square root of 3 over 2. That gives us the square root of 15 over 4. Since when we started with the fundamental theorem of calculus part 1, this means there's another part. So I'm going to call it fundamental theorem of calculus part 2. We had started with part 1, now part 2. So the part 2 says if f is continuous on the closed interval AB, then the integral of a from a to b of f of x dx is capital F of a minus capital F of b. F of b minus f of a, where capital F is any antiderivative of f. In other words, capital F prime is small f. So this is extremely important. So that's called the second fundamental theorem of calculus. Examples. Let's say we are asked to find the integral from 0 to 2 e to the x dx. So we ask ourselves, what's the antiderivative of ex? Well, it's ex. And now look what I'm going to do. I'm going to put a vertical line 0 to 2. This means you substitute the 2 in for x, you substitute the 0 in. So that would be e squared minus 1. That's a simplified version of this. Can we do more? Yes, more examples. 0 to 1, let's say x squared dx. What would that be? So we ask ourselves, what's the antiderivative of x squared? It's x cubed over 3 from 0 to 1. We always substitute the upper bound first, so 1 cubed over 3 minus the lower bound next. And that gives us 1/3 minus 0, which is 1/3. Number 3. 1 to e dx over x as another example. What we get for this? So the integral of dx over x is natural log of absolute value of x from 1 to e. From 1 means from x equals 1 to x equals e. We substitute the e first, then 1 next. ln of e is 1. ln of 1 is 0. So the answer is 1. Next one. The integral of x to the negative 2/3 dx from 1 to 8. 1 to 8. So what's the antiderivative of this? That would be x to the 1/3 over the 1/3 from 1 to 8. But the 1/3 becomes 3 to the 1/3, 1 to 8. And now how do we simplify this? Substitute first the 8, 1/3 minus, substitute the 1 next, 1/3. So how do you simplify 8 to the 1/3? 8 to the 1/3. 8 is 2 to the 3rd power if you prime factorize it. So the 3's cancel. So that gives us 2. Minus 3 times 1 is 1. 1 to the 1/3 is 1. So that gives us 6 minus 3, which is 3. Let's look at more examples. Integral from 0 to pi over 4. Secant theta, I'm changing the variable to theta instead of x. So what do we get here? What's the antiderivative for secant tangent? It's secant. And the question is, how are we going to evaluate this 0 to pi over 4? We do exactly as we did earlier. We substitute the pi over 4 first, minus secant 0 next. Okay, so what's secant pi over 4? If you don't know it, you can write it as 1 over cosine pi over 4. And this is 1 over cosine 0. Cosine pi over 4 is the square root of 2 over 2. Cosine 0 is 1. This can be flipped 2 over square root of 2 minus 1. Then multiply by the square root of 2. That gives us 2 square root of 2 over 2 minus 1. These cancel out. That gives us the square root of 2 minus 1. Next one, number 6. What about if we have y minus 1, 2y plus 1, dy from 0 to 1? Or let's make it 2. How we can find the antiderivative for such a thing? Well, to find the antiderivative for this, you must multiply first all of this out. So you distribute this 2y squared plus y minus 2y minus 1 dy. And then this gives us 0 to 2, 2y squared minus y minus 1 dy. And then now we're going to find them one at a time. For the first one, keep the 2 out. The antiderivative for this, y to the 3rd over 3 minus. Antiderivative for this is y to the 2nd over 2. Antiderivative of 1 is y from 0 to 2. I'm going to open 2 parentheses now, just so we can be careful about the negative sign. Substitute y equals 2 first. So 2 times 2 to the 3rd over 3. 2 squared over 2 minus 2. Substitute the 0 in. That's going to give me 0 for each one of them. So now this is 8 times 2, 16 over 3. This is 4 over 2 minus 2. So there's many ways to simplify this. We can write this as a 2, 4 divided by 2, and another 2, that's 4. Over 1, multiply by 3 to get the common denominator. So that gives me 16 minus 12 over 3, which is 4 over 3. Another example. Let's say I want to integrate from 1/2 to 1 over square root of 2 of 4 over the square root of 1 minus x squared dx. So what matters here is to know what the antiderivative for that function is. The first thing, the 4 can be taken out. And that gives me 1/2, 1 over square root of 2, 1 over the square root of 1 minus x squared dx. The antiderivative for 1 over the square root of 1 minus x squared, that's sine inverse. Sine inverse of x from 1/2 to 1 over square root of 2. Then substitute x in. 1 over square root of 2 minus sine inverse of 1/2. Watch how the 4 is outside. Keep the 4 out. This one here, it's pi over 4, 45 degree. What's the angle? Its sine is 1/2, is 90, no, it's pi over 6, 30 degrees. And all we have to do is multiply this out. 4 times pi over 4, 4 times pi over 6. That gives me pi minus 2 pi over 3. Over 3, 3, pi over 3. Another example, let's say we are asked to evaluate the integral from negative pi to pi of f of x dx, where f of x is given as a piecewise function, x when x from negative pi to 0, and sine x 0 to pi. So now the first thing I want to point out is the 0 thing. How come it's or equal at both of them? Because x equals 0, 0 and sine 0, 0, so it doesn't matter if we have it or equal at both of them. So how are we going to evaluate this? They ask us to evaluate from negative pi to pi the function dx. So what do we have here? We have two bounds here, or two intervals. One from negative pi to 0 of f of x dx, and the other one from 0 to pi f of x dx. So the first one is x, so negative pi to 0 x, that's the first one. And the other one is 0 to pi of sine x dx. So now for the first one, the antiderivative is x squared over 2, evaluated from negative pi to 0. The next one is negative cosine, so there's a negative cosine here, evaluated from 0 to pi. So then what we get here, we're going to go with the first one first, minus the cosine next. So for the first one, you substitute the 0 in, minus negative pi in. For the next one, negative cosine pi, negative cosine 0, or minus negative cosine 0. So that gives us 0 minus pi squared over 2 minus negative cosine pi is negative 1 plus cosine 0 is 1. Negative pi squared over 2, that's 1 plus 1, 2 minus 2. So that's what it gives us. So the answer negative, that's okay. To get a negative answer means majority of the graph of this function falls below the x-axis. As a note, let's say we're asked to evaluate an integral from negative 1 to 2, 1 over x squared dx. One thing to note about this function, note that the function 1 over x squared is discontinuous. Is discontinuous at x equals 0, which is, notice how we're working from negative 1 to 2, and 0 is part of that interval. So we cannot integrate it like the way we were doing today. So we can't for now. Later on we're going to learn how to handle such integrals. Well, we call it improper integrals. We're going to go over that later on in the next course. Another thing, if we look at the integral 0 to pi secant square x dx. Well, people say the antiderivative of secant square is tangent. Yes, that's correct. 0 to pi. But tangent is not defined. Okay, tangent, or this function here that we have, is not defined at pi over 2. Right? It's not defined at pi over 2. So we can't go straight from 0 to pi, because there's a restriction at pi over 2. So this one we can't say, oh, this you can do it. This cannot be done. Neither secant square nor tangent x defined at pi over 2. Just keep these things in mind. It could be like a true or false problem that they give you the integral 0 to pi secant square dx, and they give you the answer. You know, which if you evaluated this one, we got 0. And then also you might do the work and say, yes, it is 0, but it's not 0. Okay, it's not 0. So we need to be careful about where is the function defined, where is it restricted. And that really happens in this section, but we're going to see it more in depth in the later sections, maybe in chapter 7.